All right, there's plenty of evidence for evolution, and we're going to go through some of that evidence right now. Okay, so one example of evidence is fossil evidence. Layers of rock contain fossils. The newer layers are on top, the deeper ones are older fossil evidence. And over time, it creates a record. So the newer organisms are on top as you dig deeper, deeper through the soil layer, through the rock layer. Actually, it's not soil anymore. Through the rock layer, you're going to get evidence of older and older organisms. And you can estimate how long they have lived on Earth. And there are advanced things like carbon dating that scientists can do to actually come pretty close to estimating when organisms were on Earth. Okay, and this covers a long period of time, hundreds of millions of years. Okay, here's an example. The example of the horse. At the bottom here, we have this is 0.4 million years ago what a horse looked like. Up here, 1.6 million years later, is the modern horse. Okay, three things have evolved that on this slide. Number one, horses have become taller as time has progressed. That has meant that the most fit horses, the taller ones, are able to see predators and tall grasses better. So they were the most fit. Secondly, the kind of hoof. Okay, if you look at the bottom here, we've got basically individual toes. And now we have a hoof, and that allows the horses to run and escape predators more quickly. And lastly, the back teeth, the molars, they have become stronger and have a harder coating on them, and that allows them to grind tough grasses. So those are three evolutionary adaptations that have occurred over almost 1 million years. Okay. There's also evidence that of structures in different organisms that actually are very, very similar. We call this comparative anatomy. So if you look, we've got the human here, the cat here, the whale here, and the bat here. This is the human's right arm. This is the human's left arm. This is the cat's left front paw. So basically, it's the left arm of the cat. This is a whale's left flipper, and this is a bat's left wing. If you look at the colors, they're all color-coded. They each have a humeral bone. Humerus, 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 humerus. Yes, they are different sizes and different shapes, but they're still there. Okay? They also have a radius and ulna, like humans do. Cats do. Whale flippers still do, and bat arms still do. They have carpals, the wrist bones, in yellow. They've got metacarpals, the bones that are in the back of your hand, in greenish there. And lastly, they have phalanges. These are the bones that make up your fingers. Humans, cats, whales, and bats all have them. It's called comparative anatomy. That means that we are all related. That means that we all have a common ancestor. Those structures are called homologous structures, okay? Homologous means that they're structures that came from a same common ancestor. Now, they might not have the same function. Like, for example, the whale flippers are good for swimming, not too good for walking. Okay, they're evolutionary related. Okay, now you might think that bats and birds are very related. These are analogous structures, not homologous, because actually they're unrelated organisms. They perform the same function, but they don't have the same common ancestor. They diverged on the tree of life at different spots, okay? So they're analogous, and they're not evolutionary related closely, okay? Now, embryonically wise, fish, reptiles, birds, and humans, we all have very similar looking embryos, okay? That's more evidence. It's called comparative embryology. We also have vestigial structures, and these are structures on modern animals that have no function, okay? So, for example, some snakes and whales have pelvic bones and the leg bones of walking ancestors. Snakes and whales don't need leg bones, okay, but they're vestigial, they're leftovers, okay? Human tailbone, for example. We don't have tails, but we have a human tailbone, okay? Lastly, we can compare DNA. These are DNA sequences looking at the A's, T's, C's, and G's. You look at common genes and common proteins. For example, we're looking at here the hemoglobin, okay? So human hemoglobin is made up of 146 amino acids. These in circles, these are the differences from human amino acids. We are only 8 out of 146 amino acids different from the macaque monkey. Okay, we're 32 away from dogs. We're 125 away from lamprey eels. That means that we are very, very distantly related to lamprey eels, but we're very closely related to monkeys and primates.